So, welcome to today's review physics. So, a block of mass 4 kg causes a spiral spring to extend by 0.16 from its unstretched position. The block is removed and another body of mass 0.5 kg is hung from the same spiral spring. If the spring is then stretched and released, what is the angular frequency of the subsequent motion? Okay, the first thing is we know the formula for angular frequency W is equal to 2 pi f. So we begin by finding the force constant. The mass has been given to be m, so we're going to multiply it by gravity. It's going to be 4 times 10 equals 40. So we're having 40 Newton as our force. We have our extension as 0.16 meters. So we need to find our force constants from Hooke's law. You know that F is equals to KE. So K will be equal to F over E. That is going to be 40 divided by 0.16, which we calculate is going to give us 250 Newton per meters. So now we're going to find what is the relationship between the mass, the force constants. So we're going to use T is equals to 2 pi root m over k. So this is one of the formulas we use in simple harmonic motion, and we have to get acquainted with some of this relationship. So now this will be equal to 2 pi root 0.5 over 250. So now to simplify this better, we multiply by 10, so we have figures we could play with. So we know that T is equal to 2 pi over 5 over 2,500. So we can see that T will be equals to 2 pi root 5 over 50. Since root 2,500 is 50, so now we need to find our F. We need to find our F. So remember that F is equal to 1 over T. So we just have to F. So we'll just have to take the reciprocal of the whole of this. So taking that reciprocal gives us the 50 is coming up over 2 pi root 5. So these two cancel this, we're having 25. So F is equals to 25. So F is equals to 25 over pi root 5. So putting it into our formula for angular frequency, W equals to 2 pi F. You see here that now W will be equals to 2 times pi, that is the value of F, which is 25 over root 5. So this cancels this. So we're having W is equals to 50 root 5. So when we take conjugates, we discover that W will be equals to what? 50 root 5 over 5. This will give you 10 root 5. So we'll go with this. So we'll go to the next question. So next question says, the body timed 20 oscillation of a certain pendulum 3 times and obtained 44.3 seconds, 45.5 seconds, and 45.7 seconds. Calculates the mean period of the oscillation of pendulum. So here there are various approaches we could use. We could try to find the period individually, and we can still try to find the period. We can work with the values together. So let's take a shorter route. So we can find the mean period. We can look for the mean period, which is equals to 44.3 plus 45.5 plus 45.7. So divide by 3. So we're trying to take the mean value, adding them up. We're going to have 45. Taking the mean, we're going to have 45.166. So this is the mean time. I've been saying period. So this is the mean time. So to get our period t, know that period t is equals to the time over number of oscillation. So what is our time? Our mean time is 45.166 divided by the number of oscillation is 20. So using a calculator, we have 2.258. So approximately we're having 2.26 seconds. So again, with option D. So question 3 says a loaded spring is set in simple harmonic motion. The force that tends to restore the load to its equilibrium position is. So if you have a spring, this is a spring at its rest position. If a force is being extended to this spring, force F is being extended to this spring, stretched maybe to this position, there's a force that tends to pull it backward, which we know as the restoring force. So the restoring force. So this restoring force is due to what? The energy in the spring, the elastic potential energy in the spring. This is what causes the spring, the restoring force, to try to return it to its position of rest. So the answer is elastic potential energy. So the fourth question says, a loaded spring performs simple harmonic motion with an amplitude of 5 centimeters. If the maximum acceleration of the load is 20 centimeters per second square, calculate the angular frequency of the motion. So a loaded spring performs. So we need to find a relationship to this term. Like I said, in simple harmonic motion, we have a lot of relationship that we have to get acquainted with. So now we have amplitude. Amplitude is 5 centimeters. If the maximum acceleration of the load, so we have acceleration maximum, which is 20 centimeters per second square, and we are asked to calculate the angular frequency. So what relationship do we have? This relationship we have A maximum is equals to amplitude times the angular frequency square. So we're looking for the angular frequency square, so divide both sides by the amplitude, so the square will be equals to A maximum over the amplitude. So what is our A maximum? We have 20 over 5. So our angular frequency is going to be 4, and square root of 4 is 2. We'll have to write seconds. So the next question, question 5. A pendulum ball executing simple harmonic motion has 2 centimeters and 12 hertz as amplitude and frequency respectively. Calculate the period of the motion. So we are given the amplitude and the frequency. So calculate the frequency, calculate the period of the motion. So period is equals to the period is equals to 1 over frequency. So the period has nothing to do with this, the amplitude, so 1 over 12. So 1 over 12 hertz. That is to say the period is 0.083 seconds. So in 2 decimal place, 0.08 seconds. So this. Question 6. So the question 6 is simple pendulum makes 50 oscillations in 1 minute. What is the period of its oscillation? We know that period is equals to time over number of oscillation. So the period 1 minute. So we know 1 minute is equals to 60 seconds. So 60 over 50, which will give us 1.20 seconds. So the next question, 7th question, is similar to that of previous one we just attempted. So we're still looking for period. The number of oscillation over, beg your pardon. So the period is the period is time over number of oscillation. So time over number of oscillation. So which will be 38 over 20, which is about 1.9 seconds. Go to the next question. Question 8. A swinging pendulum between the rest position and its maximum displacement possesses a gravitational energy only, kinetic energy only, potential energy only, both kinetic and potential energy. Now we have said a simple pendulum. So if we assume this is the position of rest of a simple pendulum, this is its maximum displacement, respectively swings. Now we know that at this point it experiences its maximum kinetic energy. At the point of rest, it's experienced maximum kinetic energy, and here it experiences maximum potential energy, and here it experiences maximum potential energy. Then so it says swinging from the position of rest. So from here its kinetic energy is maximum, and the as it's swinging towards this position, the kinetic energy is reducing as the potential energy is increasing. So at this point the potential energy is maximum while the kinetic energy is minimum. So you can see that it is exhibiting both kinetic and potential energy as it swings from its position of rest to the maximum displacement. So the answer is D. Question 9. So we are going to be using the idea we just learned from the previous question to answer question 9. So from what we discussed, we said at this point it is experiencing a maximum potential energy, and at this point it is experiencing maximum kinetic energy. So an oscillating pendulum has a velocity of 2 meters per second at the equilibrium position 0 and 0 meters per second velocity at the position P. Now using the diagram below, calculate the height h of P above O. Now taking acceleration due to gravity to be 10 meters per second square. So from this idea you can see that at this point it has the velocity as 2 meters per second, and at point 0 it's having its velocity to be 0. So you can see that as it's increasing here, this is the maximum displacement. So now we see that kinetic energy here is equal to what? The potential energy. So we know that kinetic energy is mv square is equals to potential energy, which is mgh. So our m can cancel out. So our h, making h the subject of the formula, v squared over 2g. So our velocity is 2 squared or 2 times 10, which is 4 over 20. So 4/20 is equals to 0.2 meters. Going with option C. Now question 10. During a training section, two footballers passes a ball repeatedly, beg your pardon, between each other. The to and fro motion of the ball is not simple harmonic because, so we want to see the reason why this is a to and fro motion between the two footballers, but why is this motion not simple harmonic? Now, the option A says the acceleration of the ball is not directed towards a fixed point. So restoring force is not directed towards the center. Acceleration of the ball is not directly proportional to the displacement from a fixed position. So from this, you see that we know that in simple harmonic motion, the force, the acceleration is always directed towards a fixed point, and the direction of acceleration is also the direction of the force, the restoring force, which tends to pull the object towards its center. And the third one says acceleration of the ball is not directly proportional to the displacement from a fixed point. So we can see that we're going to take away this options C. So we're taking option B out because the remaining to satisfy the, so you can see now that the remaining to satisfy that acceleration is always directed towards the center of the equilibrium point, which is also the direction of the restoring. What's the next question? So question 11. The amplitude of a particle executing simple harmonic motion is 5 centimeters, while its angular velocity is 10 rads. Calculate the magnitude of the maximum acceleration of the particle. Now, we are already familiar with this relationship that talks about the maximum acceleration to be the amplitude times the square of the angular frequency. So the amplitude has been given with 5 centimeters, while its angular velocity is 10 rads per second. So calculate the magnitude of the maximum acceleration. So since our answers is in meters, we have to convert this to meters. So our maximum acceleration will be equals to the max will be equals to 5/100. That's we're trying to convert the centimeters to meter times 10 square. So we can see that this cancels 10 square, which is 100. So our A max will be equals to 5 meters per second square. Number 12. The amplitude of the motion of a body performing simple harmonic motion decreases with time because the frequency of oscillation varies with time. The period of oscillation varies with time. Frictional force dissipates the energy of the motion. Energy is supplied by some external agency. So we could recall Newton's first law. The body will continuously be at rest or uniform motion except an external force is exerted on it. So we know that is why it is called this is applied to this topic simple, because we are looking at an isolated system where no external force is being exerted on the system. Because if no external force is exerted on the system will continue in its periodic motion, like forever. So now, for this motion for the amplitude to decrease per time is telling us that another external force is disrupting the system, and there is a frictional force between the ball and the air molecules. So as they come in contact, it constantly reduces the amplitude until the body is finally brought to rest. So frictional force dissipates the energy of the motion. So the next question says, the bulb of a simple pendulum has a mass of 0.02 kg. Determine the weight of the bulb. So from Newton's second law, we know that force or weight is equals to mg. So what's the mass? 0.02 times 10, which will give you what? 0.20 Newton. So next question. The bulb of a simple pendulum takes 0.25 seconds to swing from its equilibrium position to one extreme end. Calculate the period. Okay. Let's see what it's going to look like. Now, we're just trying to look at the various position of this pendulum. So they said if it takes 0.2 to swing from its rest position, that is from here to here. So if it takes 0.25 to swing from, so let's see if after swinging towards this place, it returns towards this direction. It returns, and when it gets to this direction, so it returns to this, back to the position of rest. So we are seeing that we're looking at four scenarios. When it takes from here to this point, with the first scenario, then it takes from here to here, the second scenario, and it's taking equal time. So if it takes 0.25 seconds, then we'll multiply it by 4. So which is going to give us 100 seconds. So question 15. A bulb of a simple pendulum takes 8 seconds to complete 10 oscillations. Determine the frequency of oscillation of the body. So we know that before frequency, we're looking for the frequency. So we need to calculate the period first. And we know period is equals to time over number of oscillation. So our time is 8 over 10. So that means our period is 0.8 seconds. So to get the frequency, we know frequency is the reciprocal of the period. So 1 over 0.8. So in the calculator, this is about 1.25 hertz. The diagram below shows the position of a simple pendulum set in motion. At which position does the pendulum have maximum kinetic energy? So as you can see, this is the maximum displacement from this point. This is the maximum displacement from this point, where the potential energy is at its maximum. This place, the potential energy is also at its maximum. So we know that this is a position of rest. And this is where the kinetic energy is what? Maximum. Okay. So question 17. The frequency of a swinging pendulum is D. So this question, we can derive this question from the definition of frequency, which is the number of oscillation a body completes in 1 second. So number of oscillation the pendulum makes in 1 second. So this is D, that's D. So the next question says the length of a simple pendulum is increased by a factor of 4. So is its period increased? So know that T is equals to 2 pi root of L over G. So this we're going to look at the two scenario. The first scenario, it's the length is L, and the second scenario, the length has been doubled by a factor of 4. So let's look at the first scenario using the original length. The second scenario, and you know that period is always is linearly or directly proportional to L. So the second scenario, say that 2 pi. Now the length has been increased by 4. So we have a number on this, so we need to pull this out. You know that 4 is a perfect square, so we have to take these two out. So the square root of 4 we're taking it out, so we're having 2 pi root L over G. So we've taken out the square root of 4, which is 2. So here we have this square is equals to 2, and we know that 2 pi L over G is T1. So we see that the period has been increased by 2. The 19th question. The mass of a loaded spiral spring oscillates vertically between two extreme positions P and Q, with the distance from the equilibrium position Q. Which of the following statements about the system is not correct? So we're looking at a vertical oscillation of a loaded spiral spring. Let's say this is the position of rest, and when stretched, so let's assume this is the position when stretched. Let's look at this as the original position or equilibrium position, which is Q, of an extreme position of P and R. So which of the following? So the total energy of the system is always constant. The kinetic energy of the mass is maximum at P. So we know that this is not correct, because we know that kinetic energy is always maximum at the equilibrium position, which is at Q. The elastic potential energy of the spring is maximum at Q. We also know that this is not correct, because the potential energy is always maximum at the two extreme or maximum displacement. So the elastic position is maximum here. The momentum of the mass is maximum at Q. So we see that at Q here, we have the maximum kinetic energy, meaning that the velocity is maximum at this point. So, and the momentum of the mass, so we know since momentum is mass times velocity, mass is constant. So now if the velocity is so at this point, know that the momentum of the mass is quite maximum at Q. Oh, 20th question. The motion of a body is simple harmonic if the acceleration is proportional to the square of the distance. We know that acceleration is not proportional to the square of distance. So the path of the motion is a straight line. Acceleration is always directed towards a fixed point. Okay, this is correct. And the acceleration is directed towards a fixed point and proportional to the distance from that point. So we have these two answers correct, but we'll be going with this since this has more complete information than this, because we know acceleration is proportional to the displacement from the point of equilibrium, and we also know that acceleration is directed towards the fixed point. So since this has more information, we'll be going with this. So D. First question 21. Question 21. The period of a simple pendulum X is 5 seconds. what is the period of the pendulum Y, which makes 50 vibration. In the same time, it takes X to make 20 vibration. So the period of a simple pendulum X, so we have period X is equals to 5 seconds. What is the period of a simple pendulum Y? So we're looking for the period of Y, which makes 50 vibrations. So the number of oscillations for Y is 50 vibration. In the same time, it takes X to make 20. So the number of oscillation for X is 20. So if you can look at this, you discover that this and this has a complete information. So we see that the period of X is equals to the time it takes X over the number of oscillation of X. So T will be Tx times Nx. So we see that the time T will be equal to Tx is 5 times Nx is 20. So it's 100 seconds. So remember in the question they said that the same time it took X is the same time it took Y. So we're going to use, so looking for 2Y, we're going to use the same time, which is 100. But from the information provided to us, we said the same time it took X to make 20 oscillation, that's the same time it took Y to make 50 oscillation. So now we need to find the number of oscillation for Y, which is 50. The period of Y is 2 seconds. The period of an oscillatory motion is defined as the, so what's the definition of period? We know that frequency is the number of oscillation a body covers in 1 second, while period is the time for a body to complete an oscillation or a circle. So here I say the average of the times used in completing different number of oscillations. So that's not the period. The time taken to move from one extreme position to the other extreme position, that's also not the complete circle. That's a half circle from one extreme position to another extreme position. It's a half circle. So time to take a complete oscillation. So time to complete a number of oscillations. So the time to complete one oscillation. So the time to complete one oscillation. So we're going with D. Question 23. Well, the period of oscillation of a particle executing simple harmonic motion is 4 per seconds. If the amplitude of oscillation is 3 meters, calculate the maximum speed of the particle. So we have a lot of relationship in simple harmonic motion, so many formulas. So for maximum velocity, it's the angular frequency times the amplitude. And we know that the angular frequency is 2 pi f. But since f is equals to 1 over t, our angular frequency is also 2 pi over t. So 2 pi, our t is having 4 pi. So this cancel this, 1 here, 2 here. So our angular frequency is 0.5. So our V maximum is going to be 0.5 times 3 equals to 1.5 meters per second. So 24. Two simple pendula A and B of equal length and of mass 5 kg and 20 gram respectively are located in the same environment. The periods TA and TB of their respective oscillation are related by the equation. Now from this we know that period varies with length. So period varies with length. Period varies with length. So, but period has nothing to do with mass. Period does not vary with the mass. Understand? So, since only we have different masses, it doesn't affect the period. So the period will vertically be the same. It's only vary if the two bodies having different lengths, then the period will vary. But if they have the same length and different masses, the period will still be the same. And 5. Two simple pendula X and Y makes 40 and 50 oscillation respectively in equal time. If at equal time, so take note of this, if the period of oscillation X is 1.5 seconds, what is the period of oscillation Y? So simple pendulum, so we this is number of oscillations. So number of oscillation for X is 400. Number of oscillation for Y is 500. At equal time, if the period of oscillation, so for X, so period of oscillation for X is 1.5. And what is the period? So what is TY? So from here we can see that our X has a complete information, so we can use this to find the time. It's the same time for X or the same time for Y. So we know that period of S is equals to the time over number of oscillation for X. So the time will be equals to TX times NX. So what is our T? The time is equals to 1.5 times 400. So that will give us about 600. So since it takes the same time, it's going to be TY is going to be time over number of oscillation for Y. So it takes the same time, so 600 over number of oscillation for Y, 500. That will give us 1.2 seconds. So the next question, in which of the following graph correctly represent the relationship between the kinetic energy KIE and the displacement D from the position, Which of the following graph correctly represents the relationship between the kinetic energy Ke and the displacement from the point of release of a swinging pendulum bulb? So I want to see which of those graphs represents the graph for kinetic energy, the displacement. So we know vertically. So if this, so I'm going to be looking at just one scenario from there to here. So graph of kinetic energy. So from the point of release of A. So when we point of release, remember that it is at the point of this point of equilibrium. So to release, we need to take it at a little angle, less than 15 degrees. Now, so at this point, we discover that the potential energy is, the kinetic energy is minimum at this place, and it start increasing. You understand? So the graph of kinetic energy to the displacement, see that it starts from a point of decrease. So when it gets here, it gets to its maximum. So when it gets to its maximum, so back to this position again, see it's getting back to its minimum. So it starts coming down again. So you see that the answer is C. So see that from as the pendulum is released, it starts increasing, because the pendulum is released from the maximum potential energy. It gets increasing, and when it gets to its maximum at the equilibrium position, it begins to come to rest. The next question: which of the following statements about an object performing simple harmonic motion is correct? The max A is maximum at the extreme position. We know that we've emphasized this, that the maximum at the extreme end, the potential energy is maximum. But in simple harmonic motion, we know that the acceleration is constant at each point and is directed towards a fixed point. So we say, so the first one is wrong, since acceleration is constant at each point. So it's constant and directed towards a fixed point. The acceleration is constant, varies linearly with displacement from a fixed point, and directed towards a fixed point, is zero when it is displaced from. So we see that it is always changing. So varies linearly with the displacement from a fixed point and directed towards the center. So like this too is correct, but this has a more complete information, because we know that the so varies linearly with the displacement from a fixed point and is directed towards. So this has more complete information, so we'll go with C. (28) Which of the following statements about simple harmonic motion is correct? The selected one. So which of the following statement about simple harmonic is correct? Period of acceleration varies linearly as acceleration due to gravity. Linear acceleration varies inversely with displacement. Linear acceleration is directed to any variable point. The total mechanical energy always constant. So the total mechanical energy is always constant because at each point the sum of the potential kinetic energy is constant throughout the system. Which of the following statements about the motion of a simple pendulum is true? It is a simple harmonic motion when the angle of displacement is large. So we know that in simple harmonic motion, the angle is very small, about less than 15 degrees. So it was wrong. It possesses maximum kinetic energy at both extreme ends. You know that at both extreme ends, the potential is maximum. It passes the equilibrium position with minimum speed. We know that at the equilibrium position, the kinetic energy is maximum. So this is also wrong. It swings faster at the poles than at the equator. We know that the period of varies with gravity. Understand? It varies with gravity, and we know that gravity is greater at the poles compared to the equator. So at the poles, at the two poles, the gravitational force is higher. You know, the higher the gravitational force, the greater the period. So we can see now that it's so definitely the answer is this, because the gravitational force is greater at the poles. So at the pole, it is going to swing faster. It's going to be faster because the gravitational acceleration is greater at the poles. Which of the following will reduce the frequency of oscillation of a simple pendulum? Decreasing the length of the string, decrease the mass of the ball, increase the length of the string, increase the mass of the ball. So we know that the period of frequency is inverse to the period. And you know that as frequency increases, the period decreases. Now we know that in this both mass has no relationship. It doesn't affect neither the frequency nor the period. So we know that from this, T is equals to 2 pi root L over G. So we see that period is directly proportional to the length. So the period is directly proportional to the length. You see that 1 over F. You see that as L is increased, the frequency is decreased. So for us to have a decrease in frequency, we need to increase the length spring. But we come to the end of this solution. See you next time.